In this video, we will be learning how to represent qubits using Bloch sphere. So previously, we have looked at a mathematical way of representing them, which is direct notation. And now Bloch spheres are more of a visual way to represent them, which we will be looking at in this video. So to understand them, we need to keep some points in mind related to complex numbers. So complex number is basically z equals to x plus iy, where x is the real part of the complex number and y is the imaginary part. We can represent this complex number using a unit circle as well, wherein unit circle means that the radius of this circle is 1. The x-axis represents the real part of the the complex number, and y-axis represents the imaginary part of the complex number. So now if we have a particular vector at a particular angle with the x-axis, then we can decompose that vector into cos phi and sin phi in the x and the y direction respectively using trigonometry. So we know that cos phi represents the x part or the real part of the complex number. So over here we can replace x with cos phi, and similarly sin phi is in the direction of imaginary part or the y-axis, and therefore y can be replaced by sin phi. Over here mod z is the magnitude of this particular vector, which can be calculated as under root of x square plus y square. And we can replace cos phi plus I sin phi using e to the power I phi. And this is an equation that was given to us by Euler. That's why the name Euler's formula. So we should keep this in mind. This will be really handy ahead in this video to understand some concepts related to the Bloch sphere. So what is Bloch sphere? It's basically a sphere. It's a unit sphere. That is, its radius is equal to 1. And we can represent any qubit using this Bloch sphere. Like the unit circle can represent any vector that is 2D. Likewise, so can the Bloch sphere. So basically any point on the surface of this qubit, this Bloch sphere represents a qubit. And any unique qubit or every qubit that exists can be represented by the Bloch sphere. So we know the equation of a qubit from previous videos, that psi ket is equal to alpha ket 0 plus beta ket 1. Why? Because when we haven't measured a qubit, it's like a coin which has been tossed. So it's neither heads, it's neither tails, it's something in between. So when we measure the coin, when we stop the coin, then it will either be heads or tails, right? So similarly, when we measure this qubit, it will collapse into ket 0 or ket 1. But while we haven't measured it, it's in a linear combination of both of them. It's in superposition. It's both ket 0 and ket 1. And alpha and beta represents sort of the amplitude or the probability of it being in ket 0 or ket 1. So the probability of it being in state of ket 0 is alpha squared, and that of being in state 1 is beta squared, which has been proven in previous videos. So you can look that up if you don't know it already. Also, alpha and beta are complex numbers, and we can represent them as modulus alpha as modulus of alpha multiplied by e to the power I phi alpha. As we saw in the previous slide, and likewise we can represent beta also. Now if we are representing them like this, then we can replace their equation in this equation of the qubit. So now we've replaced alpha with its polar form and likewise beta. And now let's just try simplifying it. So we take out e to the power I phi alpha outside and get something like this. Now, there's something really interesting over here. E to the power I phi alpha can be ignored because it's global phase. It is common to the complete equation. So you can imagine it using this analogy that there is a race. Now, everybody starts from the starting point. or if everybody starts from 10 meters ahead of the starting point, or 10 meters before the starting point, or wherever, but everybody starts from the same point, then it really doesn't matter it doesn't really affect the result of the race, because everybody started from the same point. So we can ignore this global phase. But the relative phase you're getting over here by taking this term common, which is I into phi beta minus I into phi alpha, cannot be ignored. Why? Because this is like the relative position. Now, if in the race, the distance between two people is the relative distance between them, and we cannot ignore it, because that will affect who the winner of the race will be. Therefore, in the next equation, we see that we've ignored the global phase, but we've kept the relative phase, and we've taken a term phi to represent phi beta minus phi alpha. And this phi is over here in the Bloch sphere. And after I've completed talking about this derivation, then I'll talk about what this phi is. Now, next step. You can see a theta is also there in this Bloch sphere. So we will try to get theta in our equation as well. So we know that alpha square plus beta square equals to 1. We have proved this in prior videos, so you can look over there. But in simple terms, this is because of probability. We know that the probability of all the events should be equal to 1 when they are summed up together. So now there are only two possible states on measurement. Either the qubit will be in ket 0 state, or it will be in ket 1 state. So the probability of being in ket 0 state is alpha square, and of being in ket 1 state is beta square. And this has been shown in a previous video. You can look over there. So these are the two possible states that we can get on measurement, and the probabilities are alpha square and beta square. So obviously their sum should be equal to 1. Now from trigonometry, we know cos square theta plus sine square theta equals to 1. And we can replace alpha with cos theta by 2 and beta with sine theta by 2 to get this particular equation, which holds true because of trigonometry. And then we can replace these new equations in our equation of the state of the qubit and get something like. So we get this new equation, which is psi ket equals to cos theta by 2 into ket 0 plus sine theta by 2 into e to the power I phi into ket 1. This is something really different from the equation we started with. There is no alpha or beta term over here. And if we look closely, there are two terms, two angles, in fact, theta and phi, which govern the complete equation. So now if we look at the Bloch sphere, we have again two angles over here, theta and phi. And using them, we can represent any qubit state that we want. Now there are two really interesting points to note over here. That ket 0 and ket 1 are shown at a degree of 180 with respect to each other, which is not possible because we have established earlier that ket 0 and ket 1 are orthogonal. That is that they make a 90-degree angle, that they are perpendicular to each other. So therefore, to incorporate that fact, we are not taking theta over here, we are taking theta by 2 in our equation. And so this points to the fact that this sphere is not really 3D. Why? Because it is supposed to be 2D, in fact, because it is represented by just two basis states in its equation, that are ket 0 and ket 1. And if we know that ket 0 equals to the column matrix of 1 and 0. So there are just two coordinate points, not 3. So essentially this qubit is 2D, and obvious reasons, because qubit represents binary information of being in state 0 or state 1 when measured. There is not a third state, right? So this is 2D. In fact, we've just used maths so beautifully that we can represent it in 3D. So now that we've talked about theta by 2, so you can just imagine taking this ket1 and dividing it by 2. So like over here, right? So this is what we saw previously as well, right? Over here, this and this. You can imagine it like this now. And this is the particular vector that we have. So this is what we get, the Euler's formula. So it's something like that only. If you look at it, it's cos theta by 2 and sine theta by 2, like over there. And it's just representing in 2D that where this qubit is. So you can imagine it in 2D that this is like the position of the qubit, and this phi angle is the relative phase as we talked earlier. So it just represents where this qubit lies in that particular orientation as well. Like it is in 2D, and if you look from top, like if you look from ket 0, zero's direction, then it can be anywhere on the sphere. It can be anywhere with respect to this circle, this cut that you see. So basically it's a 2D vector, and then it can be in any orientation about the z-axis or ket 0. So using theta and phi, we can represent any point. So I hope you're able to understand that why it's not really 3D, but we can still represent it as 3D by taking these two angles into account. So yes, so 2 points to keep in mind is that though we can see that ket 0 and ket 1 are at 180-degree angle, but they are orthogonal. We have just used maths to represent them otherwise. And that point has in fact allowed us to represent this 2D vector as a 3D sphere. So I hope this makes sense to you. And there's this really cool image that can help you understand this concept better in like 3D. So yeah, this is the Z direction, this is Y, this is X, and these are the two most important angles, phi and theta, that are required to represent the qubit psi ket state. So this is a very important equation to remember because this is how you can represent any point on the Bloch sphere. And let's just try putting different values of theta and phi and get different qubits and just see how the equation works. So here are some examples. Now, if we take this theta and make it 0, then it means that our qubit is in the direction of ket 0. So basically it's ket 0. And it doesn't really matter what its angle phi is, because no matter what, it will still point in the z direction or the ket 0 direction. So if we take theta equal to 0, then this is what we get as an equation. And we know that cos 0 is 1 and sine 0 is 0. So because sine 0 is 0, this term gets eliminated and cos 0 is 1. So 1 into ket 0 essentially just gives us ket 0. So that is what we expected from the equation as well. Now, let's take theta to be pi degrees or 180 degrees. That means it's completely in the opposite direction of ket 0, which is ket 1. So that is what we should get. And again, angle phi does not matter in this case because no matter what, it will still point below. So when we take pi, then because of our interesting tweak in the equation, we divide it by 2. And we know cos 90 degree is 0. So this term gets eliminated. And this term is what we're left with. Sine pi by 2 is 1. So it is equal to 1. And finally, we get e to the power I phi into ket1. And because this is the global phase, therefore it's ignorable, and we get ket1. So let's just go through all of these examples. If we take theta to be pi by 2, then it means it's in this direction. And we take phi to be 0. So it means that it's moved over here. It's pointing in this direction of x. So putting the values of theta and phi, we get this ket0 plus ket1 divided by 2, which is basically a superposition state of the two, the ket0 and ket1. And the interesting part over here is that there is 50-50 chances of the qubit being in both states. And because it's 50-50, so it's sort of important. It can be anything. It's perfectly superimposed. We're not sure at all which side it will go to when it's measured. So we call this, we have given this a name, which is ket plus, which is the positive direction in that of x. Now, if we take again theta equals to pi by 2, means this is 90 degree. It lies somewhere on this circle. And we take phi to be pi, so it means it's in the opposite direction of x. And again, putting the values, we get something like this. Again, the probability of it being in ket0 and ket1 state is 50-50. It's just that the direction is negative now. And in fact, this is also a phase, but this one is not ignorable because this is relative. So again, we get 50-50 chances of it being in ket0 and ket1. So it's sort of an important state, and we've given it a name of negative ket. If we take theta to be pi by 2 and phi to be pi by 2, we get something on this direction of y. And if we put all the values, we get this. And because it's on y direction, we again find it sort of important and have given it a name of ket I plus. And likewise, if we take phi to be minus pi by 2 and theta to be pi by 2 only, then we get something in the opposite direction of y. And again, putting those values, we get something similar to the first case, the case before this one, but with a negative sign. And we give it the name of ket I minus. So these are some states that we've looked at. And now you can probably see for yourself that we can put any particular value of theta and phi and get any point on the surface of this sphere. That is, we can represent any given qubit using Bloch's sphere in a more visual way. And I hope this was fun for you and you understood this well. If you have any doubts, well, you can put it in the comment section and we will answer those. Thank you.